Machine learning is, without a doubt, one of the most transformative advancements of the 21st century. This technology allows computers to understand real world data like text, pictures, and videos. Because of this, we now have computers that can write articles, create images, and even drive autonomous vehicles. However, there are a lot of things in the real world that aren't text, images, or videos. Most real world data is complex and interconnected, forming networks that we call graphs. A graph is a network of items called nodes with some relationships or links between them. Drugs, for example, are made up of molecules, which are a group of atoms linked together by chemical bonds. Similarly, social networks consist of people connected by their relationships to each other. These are important real world concepts and can be represented very compactly with graphs. We have specialized machine learning tools to process graphs like these. They are called graph neural networks or GNNs. These are useful for many important things like discovering new drugs and understanding social interactions. However, some graph networks are really difficult to work with, even for a GNN. Symmetric graphs, for example, are tricky because to most GNNs, different nodes can look the same, because they're symmetric. Many of today's GNNs are less useful for these types of graphs because they can't tell the different items apart. Now, there are several ways to approach this problem, but my research focuses on tackling this problem with shortest path distances. This means we give each item in the graph some information about how close it is to everything else. This simple change allows GNNs to understand complex networks better and can make them a lot more powerful. However, one problem with this technique is it can be slow, especially for large graphs. The human brain, for example, is a network of about 86 billion neurons, and it would be incredibly slow to do this for all the neurons. So rather than doing this for every item in the graph, we do this for a carefully chosen fraction of the items. Even with a small fraction, we can get useful information to help a GNN understand the graph much better. Now, we have tried this on several real-world graphs, and my research has been able to show significant improvements with just this simple change. Graph machine learning is becoming increasingly popular because of its many interesting applications in medicine, traffic prediction, weather forecasting, and many other sciences. By improving the ability of GNNs to understand these graphs, we unlock many new possibilities and exciting applications for machine learning.